Alrighty then, corn children, gonna lay some theory down on ya. We're gonna be looking today at the slope of a tangent line. Oh, the conundrum. What do you mean? All right, if you've taken any math at all, you know that slope is the change in y, change in x. Change in y divided by change in x. And the formula is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So that implies that there are 2 points required for us to figure out slope. But a tangent line, by definition, touches our curve at 1 point. 1 point? 2 points. Need 2? Have 1. Oh, chaos, don't worry. Someone much smarter than you has come along before you and figured this out. It wasn't even me. So let's hear it for Sir Isaac Newton. So here's our dilemma. We have here a function, f of x. There is a point on the curve. There is some x that I've plugged into the function, and out came the answer, f of x, making the xy ordered pair. There's the point. There's the tangent line. I want its slope, but there's a problem, 1 point only. So what do we do? Well, for a little bit, for just a little while, we're going to give up on a tangent line, and we will consider first a secant line. But look how we're going to set up this secant line. All right, so here's x. We are going to move over from x a little distance. So this right here is a horizontal change, a small change in x. We can call that little gap delta x, the Greek letter delta and an x, a small change in x. Now let's be clear, delta x is not 2 variables, it is a single entity. All right, so I was at x and then I moved over a little bit more. So how far over are we now? Well, we're over x and delta x, making this x plus delta x. Yeah, I know, clever. All right, so here's what I'm gonna do. I am now at the x coordinate of x plus delta x. I'm gonna fill that into the function, and we will get another point on the curve. Now watch how we write this. The x coordinate is x plus that little bit more. And to get the y coordinate, we would take that and fill it into the function. So we have a second x and a second y. I know. Now, we have to be clear here. If I connect these, those are 2 dots on the curve. This is not a tangent line. It is a secant line. All right, but now that we have a secant line, we can find the slope of said secant line. So here's what we're gonna do. We're gonna start with the slope of the secant line. And if you recall from a previous video, this would be the average rate of change. Whoops, not rate of change. Average rate of change. Nicely done. Yeah. All right. And here's our little formula. It's our y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Interesting. Oh, do you see what I see? Silly x's, those cancel out. That's awesome. And we get this expression. F of x plus delta x minus f of x all over delta x. Okay, that's swell and all, but it's not what we're looking for. That's the slope of a secant line. So here's the question. What do we do with this slope from the secant line to turn it into the tangent line? Well, here's what Newton said. Let's make the gap a little bit smaller. I mean, after all, the slope here and the slope here aren't all that close. They're different slantiness. But if we were to close the gap a little, if we were to make this gap smaller, wouldn't that move this second point closer to the first point? So if I close the gap a little bit, I would get, I'm going to call that secant 1. This would be secant 2. And the slope of secant 2 is closer to the tangent line. So I have now two slopes to compare. I could go this one and then this one, like a progression. Well, how could we get a better approximation? I could close the gap some more. If I close the gap some more, this dot would move along the function. It goes into the function and it moves closer. And I would get a third secant line, and the slope of the third one would be closer. So I would have now 3 slopes to compare. And so I would look at the progression, slope 1 to slope 2 to slope 3, and what are they getting closer and closer to? And as I continue to squish the gap close, the gap gets smaller, making x plus delta x closer to the original x. These dots get closer, and as a result, the slopes get closer. I wonder if we've done this process before. This process of looking at numbers in a progression and looking for a pattern. Yes, that's right. That's the limit process. The second dot is approaching the first dot. The second dot approaches the first dot. We can also say, and here's how Newton did it, that the size of this gap is approaching 0. Here's all we need to do. Now this is crazy. This is crazy. What we have here is the slope of a secant line, but we can presto changeo, turn it into the slope of the tangent line by doing the following. I'm going to take that slope of the secant line and here's what we're going to do to it. We are going to take the limit and let delta x, the size of the gap between the two dots, approach 0. No way. Yes way. Ladies and gentlemen, this is a huge moment in your lives. This right here, this limit of the difference quotient is foundational in calculus. Yes, that's right, foundational. This becomes so important. It is so much more than just the slope of the tangent line. Yes, it is the slope of the tangent line, but if we have position versus time, this also becomes instantaneous velocity. And because there's so many different applications, instantaneous rate of change, I'm not spelling that again, instantaneous rate of change, that in calculus, it gets its own vocabulary and its own notation. This limit process is also known as the derivative of f of x. I know. And because that's really a lot of writing, the notation looks like that. And we shorten it verbally and say it is f prime of x. I know, that's crazy. Newton, who'd have thunk, right?